Hello, everyone, and welcome again to another seminar of the Institute of Artificial Intelligence at the Montfort University. It is my pleasure today to present you Dr. Marco Gillies that will have a talk, as you can read, on machine learning as a movement interaction design tool for virtual reality. Dr. Gillies comes from Goldsmiths University of London. And his talk will describe how the human body and his movement are far more important in virtual reality and mixed reality that has been in the past generation of technology. These movements are often difficult to design, and therefore perhaps we can try to learn with the machine learning algorithm and try to codify them. Marco is a reader in computing and director of the distance learning at Goldsmiths University. He's a pioneer of interdisciplinary computing at Goldsmiths and was a founder of the creative computing degree and has been instrumental in developing several other interdisciplinary degrees, including digital art computing and game programming. He's also the co-founder of the Embodied audiovisual interaction group. And has worked on other forms of immersive experience and embodied interaction, and in particular applied to immersive theater and performance. His recent research has been on human-centered machine learning, in which human guide machine learning algorithm interactively as a way of making use of tacit human knowledge in artificial intelligence system. So I'll give the floor to Marco. Welcome.
Okay, thanks a lot, Daniela. And just to sort of add that Daniela and I work together and have been friends since we worked together sort of years ago at UCL. So, we'll touch. There's a few other ex-UCL people from our group involved in this. So, just check. This is you are an AI group primarily. So coming from an AI background, is that right?
I know, creative technology. So we also have game AI and similar things to what you do. Yeah.
Okay. So I think both Daniela and I have backgrounds in both VR and AI. So it's good to clarify which direction you're coming from. So I will talk a little bit about my work, which is at the interface of VR and AI. And in particular, I'm going to, sort of have an interest in the sort of the user experience, the HCI of AI and machine learning in particular. So that's kind of the perspective I'm coming from, which may be a little bit unusual. So first off, I've recently made a professor, which means I don't do anything useful, and it's all done by other people. And these are some of the people. So this is the research group, the CVR, the Social Empathic and Embodied VR Lab. It's Goldsmiths that we've recently founded together with Sylvia Pan, who another old friend of Daniela's. I'm not sure if she's talked to this group before. And we have a long list of PhD students here. Tara Collingwood-Williams is the other sort of lecturer in the group, who's also completing her PhD. So this is us, and some of these people will come up later in the talk, just to show a little bit of what we do. So the fun side, so sort of as well as having a bunch of PhD students and research level work, we also have a master's, both MA and MSc in virtual augmented reality, which is also research level. They also do research, of course. Then you can see our nice lab Christmas, and of course, all our social activities aren't restricted to real life, particularly over the last few years. So we had a nice VR karaoke session where I was the massive chili, and I don't know who the big the big mushroom was, but I'll make note that these do not include the audio. I think it's much better that you do not hear the audio of our VR karaoke session. We've also got a lot of collaborations. I took a slide from Sylvia, who had a lot of logos on this, and then had to add a load more because I realized it didn't have a load of the collaborations I'll be talking about today. And maybe we'll add Montfort to this list of logos very soon. The work I'm going to talk about today is one project with Coventry University, University of the Arts London, and University of York. Another project more industry focused with Dream Reality Interactive and Maze Theory, two small game studios focused on VR and AR. And if I have time, I'll mention a project at Durham University that I worked on. So the first project is called the 4i, which I haven't spelt out, but is the what is it called? Immersive interaction design for indie developers with interactive machine learning. So I'm terrible at coming up with project names. So if I ever do a project with you, make sure you come up with the name. But anyway, it was called 4i. And as I said, these group of people, lots of advisors here. The people primarily responsible for the work were Nicola Plant, who's a postdoc on that, Clarice Hilton, who's still a PhD student with us. The project has ended, but she's staying on, and Carlos Gonzalez Diaz, who's a PhD student at the University of York, but I co-supervise him, so he works very closely with us, and a bunch of other people. So here, this project is really about how is about movement in virtual reality. So as I said in the abstract, movement is much more important in VR than it might be in a sort of screen-based interface. So essentially, for screen-based interface, we use a finger and we tap things. But in VR, we've got trackers, we've got head trackers. These can track our movements, and these can be mapped into virtual reality. And there's a whole load of reasons why this is super important for the experience of VR. So Mel Slater presented these ideas, the idea of presence in VR. I don't know how familiar you are, but the idea of being somewhere else is decomposed into a few elements. One is place illusion, which is the feeling of being in another place. And this isn't really about how realistic the graphics are or anything like that. It's really about the interactions between our senses and our movement. So the sensory motor contingencies is the technical name. So at the most basic level, when you're looking at a screen and you look away, then you see something else. Or if you move your head, the screen doesn't, what's on the screen doesn't change. Whereas if you've got a headset on, you look around and you see another, you see what's over there, in that direction in the space. And what that gives you is, this sense of simple interaction. I move my head, I see something different in a consistent way that works exactly as you would in the real world. And this connection with that the same sensory motor contingency is what gives you this incredible sense of being in a space. And then there's a sort of a secondary illusion of plausibility, which is really to do with more complex relationships between your behavior and the world. And the critical thing here is that your behavior should be similar as possible how you interact with the real world. The more you interact with the virtual world as if you would with the real world, the more it feels real to you. There are a few other sort of interesting frameworks I won't go into. Jacob's reality-based interaction is really about how you've learned from the very sort of the moment you're born, certain interactions that are based in reality in the real world. The more you can transfer that over the digital world, the better. And also the use of movement can make use of sort of embodied cognition concepts as well. So movement is really important, but movement is very different from a lot of what we do in traditionally in computing. So how we move is it's embodied knowledge. So we know how to, for example, ride a bicycle, or most of us do, but we wouldn't be able to like explain it fully. You know, we can't put it into words. You have to learn it by doing it. You can guide someone through the process, but you can't write down, you know, a detailed set of instructions that you might be able to do for installing a software library on your PC. You just can't do that and then follow those instructions and learn to ride a bike. So there's something that we know how to do this, but the knowledge is, you know, in our bodies, or at least it's tacit. We can't say it. We can't sort of bring it into symbolic form. And this has led into a lot of interesting sort of HCI techniques for doing sort of designing this sort of embodied movement interaction. I'll just mention Elena Marquez Segura and team is embodied sketching, which uses very sort of physical body-based activities to sensitize people and get people thinking, you know, with their whole bodies about an interaction, which is great, which is really sort of, you know, gets you away from pencil and paper and 2D screens and gets you really thinking about physicality. And this is something we've done a lot. But there's a problem, which is ultimately, once you've done all that good stuff, you have to implement it, and implementing comes down to code and, you know, this logical language. So if you can't, you know, if you can't put something into words, something about the movement into words, you've got no hope of really putting it into code. I mean, it's you know, you're going from an informal language, which could maybe capture some of the nuance and complexity of embodied knowledge, to a really formal language, which has no hope. So what do we do here? And, you know, what I found really inspirational is when I read the PhD thesis of my now colleague, Rebecca Friedbrink, you know, who was using machine learning as a creative tool. And she developed this tool called Wekinator, which is a machine learning tool. And, you know, I thought this sort of paragraph was really what I was looking for in terms of how to do embodied interactions. The Wekinator emphasizes an embodied approach to composition. They're using the term composition because these are electronic musicians. By allowing users to generate training examples by actually performing gestures in real time. So they would perform gestures in real time. They would, you know, give examples which went into a machine learning algorithm and then would recognize those gestures. Performing gestures in real time, as opposed to approaching the mapping creation process rationally or mathematically. So they're not, you know, you're giving examples, you're not sort of trying to create a formula, explicitly write a formula, as is required in the design of explicit mapping. So what machine learning gives you here is this ability to design by example, design by performing movements. So you're not having to sort of formalize that movement. You can use your embodied knowledge, the fact that you know how to do the movement, without having to explain the full details of what that movement is. So it's a great opportunity for using embodied movement. So what we did, Rebecca and I and colleagues, we decided to apply this to virtual reality. So we developed a VR tool for movement interaction design called InteractML, and you know, this is used to set up, you know, this is to set up a machine learning model. We used a graph, a node-based interface. So this is to set up what the features are. You can see there's a feature extractor. You can choose what inputs are. So, oh, this is a plugin to Unity, by the way. If you know the Unity game engine, you probably do. So it's a game engine, a really popular one. So we could choose a particular input. So this might be very often in Unity, actually, you know, pretty much everything, any input can be mapped onto a game object. So it's pretty normally just an object. But for example, the left controller of, you know, in your VR controller. So if you've got an Oculus Touch controller, for example, then that's, you know, you're turning that into features. So we're extracting the rotation of that object, and we're also having just a float variable as the label. So this is a this is an example of a, oh, it's a regression actually. So it's a supervised learning. All of this is supervised. So you need a sort of an input and a label. Then you've got a node which sets up all the training examples, selecting an algorithm. In this case, it's a regression algorithm. We can have neural network-based regression, k-nearest neighbor-based classification, and the dynamic time warp base for sort of sequence data. These are, relatively simple algorithms. They're not sort of cutting edge deep networks or anything, but I think that's important because the people aren't, they're training these models as part of a creative process. They're generating the data themselves. So it's not a, it's not a big data environment. The data sets are really quite small. And then from there, you can, visualize, well, you can sort of read out the outputs of the model. And the final thing is you can link it to a script to do something, in this case, a particle system. So that's not really the important part. That's the setup part. The important part is that you're training by giving examples. So this is a video they've produced. Let me know if can you hear audio? Did you hear music?
We don't yet.
Okay. Now, you hearing music?
Not yet.
You're gonna have to hum along.
Okay. I think I probably need to reshare, don't I? I didn't click the magic button.
Or I can make you host.
Share sound. Yeah, no, share sound, that's fine. Okay, here we go. Oh, now I need to enter my passwords.
Yes, we can hear you.
Interactml is a node-based visual scripting tool for designing movement interaction in Unity. Perform your movement interactions to train Interactml's machine learning system. Then instantly use your movement designs to trigger events in your environment. A tool specifically designed for artists, dance practitioners, as well as game developers. The process is quick and easy, minimal programming experience required. Use any movement input, including virtual reality controllers, hand tracking with the Leap Motion controller, face tracking with AR Foundation, body tracking with the Kinect or motion capture system, or any movement sensor in Unity. For more information on our upcoming opportunities, including artist residencies, workshops, game jams, and...
Okay, so this is a kind of like an advert for the project in general. And for recruiting people to come and join the project. So let's move on. So this is the tool, but in a sense, the tool isn't the most important part, because I think we have, as we're looking at sort of AI and machine learning now, I think it's as important to know how we're using these technologies and how we're sort of developing data as it is to know what those technologies are themselves. That's kind of my belief at the moment. And so we co-design the technology with a methodology, which is very much based on these kind of embodied, what we call body storming. So like brainstorming, but with your bodies physically moving around. And, we intended to do this very much in person, very much physical. But this all happened, we were running our first workshops in March 2020, and the pandemic happened. So we actually did quite a good job of transferring this into VR spaces like Rec Room. So we had some interesting results about how the body storming happened in VR. VR was better in a number of ways than Zoom, but I won't go into that too much. But we developed this process which integrated body storming in with training and testing the data, all of which was very physical. So there wasn't this step where you had to step out and write some code. Well, sometimes you had to write a little bit of code, but mostly it was, you know, the training of the movement was very physical. And, you know, we did some work with artists, game devs, VR creators. So we ran a series of workshops and hackathons to get feedback from them. And then we did 3 artist residencies over 6 weeks. So I think it was really important for us to really understand what happened when people use this for a longer period of time, not just a few hours, but sort of several weeks to produce a real piece of work. And, you know, actually it turned out that even 6 weeks was, you know, just enough to get people to understand the possibilities of the tool and really how to use it. And they were all sort of wanting, actually, we want to carry on more. We've only just learned how to use it. So, I mean, this is a sign that actually doing quite long-term research is really important. So we've got some examples. Bushra Bird is a London-based, you know, sort of artist interaction designer from a British Bengali background, and sort of looking at using custom sensors mapped into VR to sort of create a VR experience based on Bengali dance. Sara Torelli and Sergio Bomberg made a more sort of conceptual piece, which was about sort of, you know, the impact, you know, sort of how do you prove yourself to be human? How do you prove to an AI that you're human? So, you know, there's quite a range of things we're done with it. And, you know, I think we've got some, you know, we're still writing this up, and, you know, only going with very preliminary papers. So hopefully by next year we'll have sort of full papers. But, you know, it was actually quite easy to learn and train machine learning models. But, you know, actually, as you went into it, there are definite gaps in conceptual understanding that made it hard for them to experiment. So they were like quite stressed and worried about, you know, what if I break this? As I said, doing it for a long time helped develop those mental models. You know, just a few hours was not enough. And one of the key things was understanding data features. So yes, going through movement is very important, but, you know, it's more easier than coding, but you still have to understand things about, well, what is a data feature? What's the difference between using rotation as an input feature versus position? And what effect would that have on the whole thing? And, you know, we sort of tried to tackle that not with a technological solution, but actually by, you know, by integrating it into the body storming, into the process. So actually sort of thinking about features before you get to the computer, sort of thinking about it as you're sort of designing the movements. And, you know, another thing is that sort of having examples of graphs, you know, sort of is very, I mean, this is a lot of learning of computing stuff is very example based. So I think having sort of examples to scaffold it was really important for new learners of machine learning. So that's kind of one project. You know, this is quite it was a 2-year project, and we've still got lots and lots of data to do, but I think it's something that gives insights about both how useful it is to use machine learning in a creative context, for movement interaction with people who aren't machine learning engineers, who aren't really even coders. You know, it can be very valuable, but also that there are, you know, big challenges that could need to be solved, both in terms of technology and in terms of how we kind of educate people, how people learn. I want to move on to a second project, which is related. So, I mean, it's still actually down to this idea of movement interaction. And so if you know, one of the most complex, most challenging, most sort of embodied, most tacit examples of our bodily expression is our social body language. So nonverbal communication, how we use gestures, facial expressions, eye contact, head nods, posture as a way of, within the context of a social interaction, is a way of communicating, but often not explicitly. So we're often, you know, sort of, we'll make a gesture, or we'll have a certain posture, and that says, you know, that communicates something, but we're not even really thinking about what our body is doing, because we're thinking about what we're saying, or we're thinking about what the other person's saying, or typically we're thinking about what we're going to say in response to whatever the other person's saying. So there's lots of sort of actually there's lots going on that we're not even aware of, and we're not even consciously aware of in the other person, but we get an emotional response to it. So we can sort of tell if somebody's understands us or is annoyed with us or is happy with us without really paying much close conscious attention to what behaviors that person is exhibiting that allows us to do that. So having that, all of this is a really strong example of what I was talking about earlier in terms of embodied tacit interaction. We can do it, but we don't know how, and we can't say how. So everything I've just said, like 100 times more for bodily interaction. So we're looking at this kind of scenario, a person in VR interacting with a virtual person in a way that, body language makes sense. So, the virtual person has to sense what's going on, understand it in a certain way, and respond with their own body language to a human being who will respond to whatever body language that is. The thing I didn't say, of course, is that not only is the body language important, it's an interactive cycle. So it's responding to what the other person is doing. So it's not just enough to play back some really nice animation of body language if it doesn't make sense in the context of what somebody's saying. So, like a crude example is a character grinning really happily at you while you tell the character that, your mother has just died. That's just completely inappropriate behavior. I've been kind of working on this problem for years and years and years, sort of 20 odd years now. And, I think what's really interesting is looking at how we can, we need to capture, this behavior, this interaction, and we need to capture it not as, because it's an interactive cycle, it's not a single person capture. It's, how you have to capture details of the entire interaction. So recording an entire interaction, then having, use that as a synchronized data set of two people, maybe different features. One person fully motion captured, one has just the audio, train a machine learning model, and then, you can use that model to create a virtual character. This is the general framework that I proposed quite a long time ago. And we've done examples we've worked with UCL to, on a project capturing sort of, quite high resolution data of, multimodal data of social interactions. And we've done a load of projects that map those onto characters. I'm going to talk about one project which I think is quite interesting, it's quite recent, which was, well, it's not that recent, it was pre-pandemic, but is an interaction, it's an Innovate UK project that was working with two games companies. So this was actually in the context of real game development. So it was with Maze Theory, who were developing a VR game based on the Peaky Blinders franchise, and Dream Reality Interactive, who do a lot of sort of interactive sort of AR and VR games. This was with Sylvia as well. And so the two people at the top are Ross Harding of Maze Theory, CEO of Maze Theory, or CTO or technical lead of Maze Theory, and Dave Lanyard, CEO of Dream Reality, who are main collaborators. And in the bottom left is Christina Dobre, who did most of this work. So she's a PhD student at Goldsmiths, but she was also an intern at Dream Reality for the purposes of the project. So let me wait a sec. Let me go through this project. So the idea here was that we're going to capture data of a real person interacting with a virtual person, and see whether the real person is socially engaged with the character. So in a typical game, a narrative game, the character's just not aware of you. So they can be doing a monologue, but you can do whatever you like, really. So you might typically kind of run around the room, sort of throw things around, open the drawers, see what you can find, while kind of listening to this thing in the background. But that's clearly not what you would do in real life. I mean, that would be incredibly rude thing to do. So what we want to look is actually gameplay, which forces you to, forces in which you can. A key part of the gameplay is to win over a character as you would in real life. So you have to pay attention to the character, you have to listen, you have to be engaged and convince this character that you're a good person who's going to help her. So we did this. I mentioned in the previous slide, 2-person capture. One of these people was a virtual person, but we'll see. So there was, in the capture process, it wasn't actually 2 people, but it's still very important to capture data about this character. So I'll play you Christina's video.
Understand how humans interact with each other and can say, from their body language, whether they are socially engaged or not. In virtual reality settings, this helps maintain plausibility illusion, but it's difficult to implement, as our judgments are subconscious, so we cannot come up with a set of explicit rules. In this work, we collaborated with 2 game studios and developed an immersive machine learning pipeline for detecting these kinds of human-defined social attitudes in VR games. First, volunteers took part in a social interaction with a virtual character. Next, an expert annotated the social interaction in the same immersive medium. This data was then used to train a machine learning model. We considered different model configurations, out of which the one that is pre-trained and with a temporal memory performed the best. In terms of input data, we trained it on raw features, such as head position, as well as psychologically based features, such as the distance between the user and the character. The model using the raw features could not generalize to different virtual character positions, whilst derived data performed with 83% accuracy. This work contributes to the field of socially responsive virtual characters, offering a design by example tool for immersive machine learning, to detect abstract social attitudes in VR social interactions, and allowing future VR games to be more engaging, immersive, and inclusive.
Okay, so there's a few points here. The critical point is that all of this, capture came in the context of VR. So you were immersed. People were immersed in that environment, and we gave, for the training data, we gave them quite different instructions. So sometimes they're told to pay attention to the character and convince her you're a nice person, or the opposite would have been try and find sort of remember as many objects as you can from the environment, so take them away from the character and distract them. And then before either of those 2 examples, we just gave them do whatever you want, in which case a lot of people just threw objects around, as you can see, because they were mostly gamers. I thought I had quit those slides. So I won't go very much into this, but I'll sort of break down what the pipeline is. So first off, we collect data in a 2-stage process. So first off, a player interacting with the virtual character. So the player is in the real virtual environment, interacting with the character, and we record what they do. That's the player representation. Then we can play back that experience. So in VR, and an annotator annotates it. So the idea here, well, I'll come back to the annotator. The idea here that this annotator is actually the interaction designer. This is the creative role here. So they can look at what player behaviors are doing, and then this process of annotation becomes the process of determining what the gameplay is. I'll come back to it in a sec. The next stage, I won't go into very much detail. It's an imitation learning, deep neural network-based imitation learning. I can go into a bit more detail later. And then the idea is, which we never quite got to, is apply that model to a virtual character, so that then the virtual character would recognize how engaged this person is and respond in some way. So this comes back down to this kind of problem we had at the start, which is that you've got these very complex, subtle subconscious behaviors. And we have to judge, well, are these people being socially engaged or not? And so on one level, like, you don't want to capture, don't want to explicitly rule, this is, if you nod your head, you're socially engaged, that will capture some of it, but it's not going to capture all of it. So you want it to be data driven, and you want it to be machine learning. But actually, the fact of labeling it and determining what it is a really important creative part of that. Now, we could try and use the player's own judgments of what they're doing, and that is an approach. But actually, really, this is a game, and it's a creative game design process. And really, in a game, it's the game designer whose job it is to determine what kind of behaviors they want from the player. And so we take a creative director, in this case, well, theoretically Russ, it wasn't actually Russ who did the labeling, but a creative director like Russ Harding would be making these judgments. So he's not trying to get to anything objective. There is no objective measure of social engagement. It's trying to be a subjective creative judgment. And so he would label work, and based on that data that was collected, it all goes into a machine learning model. And then once we have that machine learning model, that can judge further data and go into the virtual character. So Russ didn't label it, it was actually Christina, but that was the general idea. So that's second project is, an example of applying this general framework of machine learning as a creative tool, as a way of doing, tackling these kind of embodied subjective measures in a different way. So it's a sort of more complex pipeline than the 4i, and tackling more complex behaviors, and working with real game studios, which is really insightful. I'll maybe, if it's okay, I'll just spend a couple of minutes doing one last project, which just
Sure.
This is actually, sorry.
Yeah, fine, thank you. Yeah.
This is a bit less related, but and it's less my work. It was actually conducted at the University of Durham, but I was a co-I in this project, and there's two reasons I'm talking about it. One is part of my role as co-I is to publicize this work outside of psychology, so my collaborators were almost all psychologists, and the other is that we've just got follow-on funding. We've got a second project with Dorothy, which will build on some of these ideas. So just to go through the people, Hayley Dew is the first author. Hayley Dew, Jana Gottwald, and Laura Ashley Bird were the three postdocs on this project. Harry Brenton is a VR developer who I've worked with over the years, and he did some of the technical work. And the co-I is Dorothy Cowie at Durham University. So the idea here is really about embodying yourself in a virtual body. So we've got these, I don't know how familiar you are, but we've got this idea of the rubber hand illusion, the fact that you can convince yourself, or you can be convinced that a rubber hand, a fake hand on the table is actually your real hand. So on the left is the rubber hand, the right is the real hand, and they're being touched exactly synchronously. So you're feeling the physical touch that's happening to the virtual hand. You can't see the rubber hand. You can't see your real hand. You can only see your virtual hand. And this gives you a sense of can I go back? So I won't show it. So this gives you a real sense that this rubber hand is yours, and you saw at the end, they tried to hurt the rubber hand, and the person pulled back, and they felt a sort of real kind of pain there. And you can do the same thing in virtual reality, and this is from Mel Slater's lab in Barcelona. It gives you a very similar sense, and getting onto other kind of illusions. This was that's not what I wanted to
One reason was because...
No, I don't want that. Okay, so, but what you can then do is generalize this to the whole body. So you can then sort of have, you can really feel that another body is your own, especially if you can track those body arms. And in VR, it's actually much more powerful. Rather than touch, you have this sense of the movement being coordinated between the real and virtual bodies. So this is an experiment. It's quite an interesting one. It showed that being embodied, a white skinned person being embodied in a dark skinned avatar reduced implicit racial bias, which is a really impressive finding. I won't go into much detail. I won't go into detail about this one. But what we did, Dorothy's interest and the other colleagues, Haley, etc., was what happens in children. So they're all developmental psychologists, and they're interested in, what does this show us about how children's body schema, body sort of representation changes over time. So they ran a study with children aged 4 to 14 in a museum. They were popping bubbles in this fun fair environment. And what they found is that it worked. People felt a sense of embodiment, and even sort of they felt it when the movement of the hand was synchronized with the virtual hand with the real hand, and even if it wasn't perfectly synchronized, they still felt it. They could feel this with a virtual block, so this cross rather than the hand. And they said that the block felt more like a tool than a part of their body. So, there's some interesting results. This is shown to be a really promising way of understanding both the medium of virtual reality and, children's development and body representation. So this is a project. We've got some more funding, and we'll be starting a second project with Dorothy in the autumn. And actually we're advertising for postdoc right now, if there's anybody who's interested in doing some VR work of this kind. Okay, I will stop sharing. And do we have any questions? Yeah, thank you. Any questions?
Thank you very much, Marco, and congratulations for being again. So to remind me that you're a professor now, so congratulations.
Yeah, well, fairly recent.
Yes, I would like to thank you. I'm going to stop the recording, and we will ask a question to the floor.